Okay. So, we discussed what Gâteaux variation is. Now, let us complete the example that we took in the last part of the lecture. So, again I would take this functional which is j equal to 0 to L y prime square plus 1 with a square root divided by square root of y dx. So, that is our functional. We want to minimize this functional which is the Brachiost-Ockham time with respect to y of x, right. And our definition of Gâteaux variation is this delta j y. Necessarily we should have an arbitrary function h which is what we said is the d by d epsilon of j. Instead of y we have y plus epsilon h and then substitute epsilon equal to 0. Let us do this where I want to take the derivative d by d epsilon of the integral 0 to L, that is what our functional is, and wherever y is I have to put y plus epsilon h, and likewise instead of y prime I have to put y prime plus epsilon h prime, because we are replacing y with y plus epsilon h. So, y prime should be replaced with y prime plus epsilon h prime. Epsilon is a constant with respect to which we are taking derivative square plus 1 dx. Okay. This is our Gâteaux variation. So, this is when we substitute epsilon equal to 0, that becomes our Gâteaux variation. Okay. Gâteaux does not have epsilon because epsilon tends to 0, right. Now, if you see we are taking derivative of an integral, we can interchange the integration and derivative operation. In other words, I can put the integration outside and take the derivative inside of the derivative integrand. So, I can say square root of y prime plus epsilon h prime square plus 1 divided by square root of y plus epsilon h, okay, and dx, and then I substitute epsilon equal to 0. So, you can see the order of differentiation integration is interchanged here, and that is valid when the limits here we have 0 and L, if they do not depend on this epsilon, okay, then we are allowed to do this, right. Now, this is if you say whatever y prime h prime y h are, you can definitely derivative of this ratio, right. So, this is the ordinary derivative that you take with respect to epsilon, you do that and then substitute epsilon equal to 0, then be left with this Gâteaux variation which will still be in the form of an integral. That is something we need to take note. So, if I take derivative of this now, I would be doing using the quotient rule, I have to do 0 to L. So, I would do square root of y plus epsilon h and take derivative of the numerator, then that will be d by d epsilon. If I expand all that I will get something. Right now I will just write d by d epsilon of square root of whatever we have over here, and then we will say this is all the numerator minus and then square root of whatever we have over there, trying to derivative of, let us say this one I will call this is numerator, let me call this nu, this is called denominator d, here I will have the numerator and here I will written denominator. Denominator see this will be now numerator minus derivative of the denominator, right, the d, and then divide by denominator square, you do all that dx, okay, and then substitute for epsilon, because epsilon is there, you substitute epsilon equal to 0, you will still be left with an integral, okay. That integral will be your first variation. So, first variation is also an integral, okay. As we take up more examples, then you will see how we can do this routinely, and be able to use it to find the minimum function. Okay. Now, as we just mentioned in the last half of the lecture, we have to talk about this second one called Frechét differential. Frechét differential is defined slightly differently from the Gâteaux variation. So, here let us write it down in case you cannot see the small font. Here we do not have epsilon, instead we take this arbitrary function that does not go away. We say that that arbitrary function's norm goes to 0, and what we have in the numerator and the denominator are, in the denominator we make that to be the norm of that function h, and in the numerator we put down y plus h, no epsilon, minus jy, then minus dj yh, and say if this limit is equal to 0, then this dj, so that the one that we write dj yh, we say is the Frechét differential. Okay. So, when this Frechét differential exists, meaning that this limit exists and it is equal to 0 and we are able to find dj, then Gâteaux variation is also guaranteed, but other way may not be true. So, Frechét differential is more demanding because we are making the norm of the arbitrary function tend to 0, we are dividing by that norm and trying to make a limit vanish, that is become 0. If you can define such a j, then you have Frechét differential. Okay. And there are some nuances for this, that is sometimes this Frechét differential, instead of making, if you look at the what we have in the limit here, we are not saying the norm of h tends to 0, instead we are saying h tends to theta here. So, if you recall in our vector space definitions, this theta is the null function, that is the additive identity in the function space or vector space. Okay. Here we are saying that h of x tends to the null function, null vector or null function, whereas the definition, the ratio we are using norm of that. Okay. So, that is the another way of defining Frechét differential, and this Frechét differential, unlike Gâteaux variation, they are linear, meaning that if there are y h1 h2, if we take, we can make that as, let us say we have a Frechét differential with let me change the color. Okay. So, here we have, if you notice, we have not just one h, we have a1 h1 then a2 h2, then you can write it as a1 times Frechét differential of h1, h1 is arbitrary function, a2 times Frechét differential of h2. So, this holds, that means that linearity holds for Frechét differential, and so it is for the Gâteaux variation, because Gâteaux variation being a first order thing, it is linear, just like when we have a function f of x, when I take the gradient and multiply it by delta x, that is a first order term, that is a linear term. Similarly, the functional that we get, which is Frechét differential or Gâteaux variation, they are linear. Okay. And there are this continuity requirement also. How do you define continuity of a function in a for a functional? We say that for the functional dj differential less than or equal to c times the norm of the arbitrary function h of x. If such a c exists, then we say the Frechét differential satisfies the continuity requirement. So, basically there is a parallel to normal gradient that we defined, that same thing we can do for Frechét differential and Gâteaux variation. There is another thing called Frechét derivative, this is another little term. Basically what you say is that we just define the Frechét differential dj, if we take the absolute value of that, because remember j is a functional and Frechét differential is a functional, Gâteaux variation functional, you can take absolute value because that is basically real number. That absolute value if you take, if I can write that as j prime y, that is called the Frechét derivative, and we have to take this norm of this h, which will also be a number. So, here there should be a norm, then that becomes what is called the Frechét derivative. Okay. And as we said that when Frechét differential exists, then that is also equal to Gâteaux variation. Okay. We can have Gâteaux variation exist, but not Frechét differential, but when Frechét differential exists, that automatically implies that Gâteaux variation exists, and then they both are equal. And there is a little reasoning as to why it is so. So, all we are trying to say is that when you think of that limit that we used in the Frechét differential expression, j y plus epsilon h minus j of y minus epsilon dj y h, okay, then that is equal to the error term that may be there in it, that E y epsilon h times the norm of h and this absolute value of epsilon. This is true, this is one of the properties of Frechét differential. So, in the definition of the Frechét differential we did not have the epsilon. Now, if you say included epsilon, then that thing will not be equal to 0. When it epsilon tends to 0, then we said divide by epsilon tends to 0, we said that is Frechét differential. Now, we are saying differently, this is one of the properties of Frechét differential, where this quantity on the left side is equal to the quantity on the right side, that is this little error that will be there times norm of h times absolute value of epsilon. Okay. Now, this one if we rearrange slightly, so we got that epsilon that was there on the right hand side here and take this dj over there, then we get something like this. Now, as epsilon tends to 0, this particular thing goes to 0, that is this whole term goes to 0, then what we have, this is nothing but epsilon tending to 0 is Gâteaux variation equal to Frechét differential. Okay. There are some operations that you can do with Gâteaux variation. So, here we are saying that when you take j, a particular integrand f that depends on y of x, its first derivative and x. Okay. If we have something like that, I have j, okay, I have this j, okay, I think it went into another mode, looks like it. Okay. I have this j, now it is from x1 to x2, this is our functional f, x also is shown, but we do not have to show all the time, y of x and first derivative of y dx, okay, where y prime will dy by dx. Now, we already said that if you want to get Gâteaux variation, that is delta j y and this h, okay, this is y and h, which involved that d by d epsilon and all of that, we said d by d epsilon of j y plus epsilon h, where epsilon tends to 0. Okay. So, if you want it more like a mnemonic or what sometimes people call delta operation, okay, you can just follow this now. So, where we had this function, the f, we have instead of y we replace with y plus epsilon h and y prime with y prime plus epsilon h prime. Okay. Now, you need to take derivative of this and then substitute epsilon equal to 0 with respect to epsilon. Now, again what we have done here is we have interchanged the order, this is differentiation and then we have integration. What we are showing here is integration and then differentiation. When you do that, so what we get here, if we use the usual chain rule of differentiation over here, because now this integrand depends on y plus epsilon h and there is also y prime plus epsilon h prime. So, we can write it as like this. So, here we have dou f by dou y plus epsilon h times h plus dou f by dou y prime plus epsilon h prime h prime. Okay. So, what this means when you substitute epsilon equal to 0. So, note that here we are substituting epsilon equal to 0. Okay. Then epsilon equal to 0 here and here, it becomes simply dou f by dou y times h dou f by dou y prime times h prime. So, we are simply doing chain rule. Again if you go back here, so our integrand here when we integrand is d by d epsilon of f where y is replaced with y plus epsilon h, y prime is replaced with y prime plus epsilon h prime. We are taking derivative of that. We are not worried about integration now, we are focusing only on this term, that is d by d epsilon of f, which is now a function of, we are not writing x because x does not depend on epsilon as yet, epsilon h, and then we have y prime plus epsilon h prime. When you have something like this, you want to take derivative, you use chain rule. So, we have this function depending on this first. So, you say dou f by dou of that times that function, right, and then this is derivative with respect to that and then derivative of that. If you do this, what we get here will be dou f by dou y h, dou f by dou y prime times h prime. Okay. We are taking derivative with respect to epsilon. You remember, when you take derivative of this with respect to this first, we get dou f by dou y plus epsilon h into d by d epsilon of y plus epsilon h, and then we substitute epsilon equal to 0, right. When you do that, what we get is, what will this be with respect to epsilon? That simply will be h, right. That is why here we have h. Likewise, this would be derivative of this f with respect to this and the derivative of this quantity, that will give us this epsilon h prime. So, in other words, if you just want to blindly do it, the Gâteaux variation can simply be written, if you have a integrand that depends on y, y prime, y double prime, y triple prime and so forth, you have to do like a partial derivative. So, here when I take dou f by dou y, I should forget that f contains y prime, y double prime and so forth. I should focus only on y, treating that as the variable, everything else being constant. Similarly, when I do dou f by dou y prime, I have to forget the fact that y also has y, y double prime, y triple prime and so forth, and each of them you do it and then write it this fashion. Then this partial derivatives, if you use that, then you can easily write this variation. It is exactly what we said is d by d epsilon of j y plus epsilon h, where epsilon tends to 0, and the definition of the Gâteaux variation in terms of limit. All of they are the same, but this is easy to remember. Okay. This is what you would need to calculations, but you should verify that this is same as that. That basically comes from this definition. Okay. Now, there is one more concept called variational derivative, which is also useful to discuss, and this one right now you take it for granted. Okay. This later we will see how this comes about. Delta j by delta y is called the variational derivative. It is the equivalent of partial derivative for calculus of variations. Okay. In other words, when do we take partial derivative? When you have multiple functions, right, multiple variables. If you take with respect to one, that becomes the variational derivative, which is given by a something that looks strange now, that for you this one is going to look strange. We will come back to this to see what this variational derivative means. Okay. Variational derivative. Okay. So, this requires a little bit of discussion, where we want to look at a function, okay, this variational derivative. Let us say I have a function y of x, right. So, this is y of x and this is x, I have some function. What if I perturb this function only at one point, let us say this is x k, only there I have perturbed, right. Then this function becomes like as if it is a string, we are pulling it up. So, what was this function suddenly becomes this, and this area that is shaded is denoted as delta sigma k, because I have perturbed the function at x k. Because of this, what is the change in my functional? This is only a y that we are doing, but remember that our functional depends on y and its derivatives, right, how many ever there may be, right. Now, if you take that and approximate that, when you take this j and try to perturb it at, let us say x k, and you do that perturbation at every point. Okay. You say that you do not know what this height, this height, this height, you are discretizing. When you do that and try to consider that total change there, you can write it as summation of this thing, okay, the function, times x k plus 1 minus x k. This is more like delta x, right. That is the small interval that we are taking. Okay. If you notice, we have x k, y k, instead of y prime, what we have put here is y k plus 1 minus y k divided by x k plus 1 minus x k. It is basically finite difference approximation of y k. If you notice this quantity here, it is nothing but y prime. Okay. So, I am taking this j, integration being turned into summation over a discretized set of intervals. Instead of taking the continuous 0 to or x 0 to x final x f, we are making it function at specific points, and everywhere we are trying to see what happens if I perturb a little bit, okay, and get this j changed, j n or j nu. When I do that, I get this. So, we are replacing this y prime with y k plus 1 minus y k divided by x k plus 1 minus x k. Instead of taking different intervals x k plus 1, k minus 1 and so forth, if I make all these intervals equal to 1 called delta x, I can write it like this, equal interval, no loss of generality here. Okay. Now, this particular thing we have to take partial derivative with respect to this y k. So, now what happened is that our functional j, which was a function of the continuous function y, instead of that we have y 1, y 2, y n, which are the heights that I put. This is y 0, this is y 1, this is y 2 and so forth, right. This is y 0 over here, this is y 1, this is y 2 and so forth. I can take derivative of this because you want to minimize that functional with respect to, let us say, particular y k. It is a normal partial derivative. Okay. If I do that, in this summation there will be lot of terms as k goes from 1 to n. Okay. So, if I take derivative with respect to y k, we will be left with only 3 terms. This is the first term where we have y k, and also in the y prime, that is, if you look at this, we have this approximation is y prime, this quantity is y prime. We take respect to y k first, and then we take respect to y prime, in which y k is there, and then y k plus 1 also will exist when I take respect to k minus 1, k is equal to k minus 1. So, if I take that, that will give me 2 terms. This has a minus sign here because now we are taking derivative with respect to x k, this is k minus 1. When I take that, I had k. Now, when I take at k, that I will have this minus y k, that gives me the minus sign over here, whereas this is plus sign here, because when I take at k minus 1, this would be y k. Okay. So, basically you have to look at all the terms or think about all the terms in this summation and try to understand that we get 3 terms, we take derivative with respect to y k. Now, this one I am dividing by delta x. Okay. So, I am dividing by delta x, there is this delta x, okay, that goes away, this term will be without delta x, and these 2 terms will have delta x. Okay. Now, we go to the next level. Okay. Now, if you take this quantity and talk about what happens when I make this delta x go to 0, right. We are taking limit where delta x is tending to 0, okay. Then what we get is called the variational derivative, right. So, the variational derivative, the way we get, now we see what we get as f y. What I mean by f y is that when I write f y, our notation is that it is dou f by dou y. Similarly, here we have f y prime. What that I mean is dou f by dou y prime. How did you get this equation 5? It actually is nothing but what we have over here. Okay. If you see this one, this is f y, meaning dou f by dou y, and this one, this is f y prime, and then f y prime, this is at x k minus 1, this is x k divided by delta x. Basically this becomes d by dx of f y prime. In other words, this is d by dx of dou f by dou y prime. Okay. So, that is what we have here. So, the directional derivative is f of f sub y, that is dou f by dou y minus d by dx of f y prime. So, this becomes our variational derivative. So, at every point, if you want to know at a particular point, if I perturb a function, what will be the change in the functional is nothing but this variational derivative. By the way, what we have done in the last few minutes is how Euler had derived what we now call Euler-Lagrange equations. Okay. So, this variational derivative, again delta sigma, if you recall what we said, if I have a function, okay, at a particular point, if I perturb it slightly, okay, then I will have little area, I am pinching that, right. If I take this function and I pinch only one point, I will get like this, right, the new function. So, new function is going to look something like that, we have pinched it there. Now, because of this, by the way, this is our y function. So, this is our y of x, this is x, right, this is our x. Okay. Now, when I pinch it at a particular point, that area is delta sigma, that multiplied by the variational derivative will give me the change in the functional itself. Okay. So, this also helps us derive what we will call Euler-Lagrange equations, but this one is variational derivative. Okay. So, what we have discussed in this lecture are several. One is Gâteaux variation, and then Frechét differential, and then we had something called a Frechét derivative, and then we discussed what is called variational derivative. All of these are concepts required to establish necessary conditions for calculus of variations, where we say that first order term should vanish, which is what we will discuss in the next class. So, that we can do routinely lot of examples, so that you can understand how to arrive at the necessary condition and use it to find the function that minimizes. Thank you.